Hello, students. This is Mr. Gilmore with the 1.6 Geometrical Postulates lesson. We've now, in our system, have only encountered terms and definitions, right? We pointed at objects, we gave those objects term names, and then we gave them words that talked about what they meant. Well, now we're actually going to be adding something different to our system today. This next thing we're call is what we call a postulate. We'll look at the definition here in just a second. But what we want these postulates to do, there's actually like four-dimensional things that we want for postulates. The first thing is, and I want to make this one as kind of plain and simple as possible. But the first thing about a postulate is that it's really a choice. It's really to choose to add something into our system, and it's really we're choosing a truth that we want to add into our system. And so with that choice, there are going to be consequences, not necessarily good or bad, but just simply because we've made a decision, there are consequences. So the first dimension of a postulate is that it's choice. Second thing that postulate brings is usually it brings an additional property to, which means it adds something to an object that the object does not inherently have, such as measure. We're going to see that measure is something that we associate given to an object rather than that inherently the object has. Um, so that's something that a second kind of dimension of the postulate, which is it's an additional property. The third thing that we are going to encounter with postulates is that it's kind of going to be obvious. It should be something kind of like a well duh moment that when we make a statement, we're like, oh yeah, that makes sense. That's true. And so postulates really do need to be obvious whenever we make them. And the last thing that we consider postulates to be is that they're fruitful. We get a lot from them. That they're not just going to be here's a truth and then we don't ever mention of it ever again. We want to actually encounter these over and over and over again, such that they produce something for us. All right. So if you need to at any point in this video pause, I just want to encourage you to do that. A lot of it is going to be vocabulary, and actually at this point in time with our system, you will be receiving what's called a postulate theorem handout. And on this postulate theorem handout is going to be a list of our initial postulates that we'll use for semester one. Let's go ahead and jump into this lesson, and we'll look through several postulates and talk about what they do for us. So the first slide here we have is, of course, pointing at or using this definition of what is a postulate. Postulate is a basic self-evident assumption. So this is something that we don't have to justify. It's not something that we have to argue. It's just simply that it has to be true, right? We accept this as a truth and we move on from that. And again, I've made mention of this already, but it does have to be obvious, right? The last little statement there is that postulates do need to have this sort of self-evident notion to it where I don't have to convince you. It's just it is and it is, all right? And that's kind of what a postulate is. But again, this dimension of it being an additional property in our system. And again, we want this to be fruitful. So our first postulate we're going to be looking at is actually the most fruitful of all of our postulates. It's the first one we have in our list. It's called the line existence postulate. For any 2 points, there exists a line that passes through them. It is unique. So if I were to place 2 points on a board, and you see down below we have point A and point B, and I were to send a line through them, right, which means again that the points are on the line, that if I were to place 2 points, there exists one line, right? It is unique, and that line does exist, and it passes through those points. We have the ruler postulate. As I mentioned earlier, that one of the properties that we like to associate with segments or even angles is to give it measure. Well, the ruler postulate does two things. It has two clauses to it. And the reason why we call it a ruler postulate is because you're probably thinking of that 12-inch little ruler that we typically get out and we measure lengths with it, either in inches or centimeters, depending on what it is. We use this term ruler to give that sense of idea of that we can measure with this postulate, that we know that every segment has a length, which means it has a measure, and that we also can make measure with this postulate. And so when we're never going to actually touch a ruler in our class, but it just gives us the sense of what does it allow us to do with segments. It allows us to, first of all, know that it has measure, which means that we can associate measure with our segments, but it also allows us to make measure. So down below, we can actually roughly sum up the ruler postulate into two statements. It can measure and make measure. That's what it can do. All right. So let's say I wanted to measure out my segment AB. I know it has a measure, say it has length of 4. And then over here, let's say that I had this length of 6. I started with the length of CD. Well, I can cut out a measure of length 4. I know that there must be a length 4, so I can place a point E such that from C to E, there's a length of 4 there. So I'm making measure there. That's another way that we can use the ruler postulate. Okay, along the lines with segments, because now segments have measure, we can use what's called the segment addition postulate. Let's say, for example, we were handed a segment, let's call this segment AB, and we place a point C between points A and B, which means it lies on the segment. That point C then divides our segment AB into two subsegments. Well, each of those two subsegments have measure. Let's add those two subsegments together. It adds up to the whole. So we have segment AC plus segment CB is equal to the whole measure segment AB. You'll note that after the segment addition postulate, there are three letters at the top. It says SAP. Not all postulates or theorems will we have a short acronym like we use here. So if you do see that, I encourage you to do use that. But if you don't see that, then do not try to simplify. We need to then write the entire postulate name out or the theorem name out. So do not attempt to simplify that on your own. Okay, needs to be. When I get the little shorthand, that means that's an appropriate shorthand for our postulate here. So this is, if you, for now on, if you want to write segment postulate all the way out, that's totally fine, or just simply write SAP. Let's go look at now measure for angles. Now, measures for angles, we've already defined what the unit of measure is going to be. It's going to be a degree. And so for every angle, all angles have measure, and that measure has to be between 0 and 360. So what does that allow us to do? That means we can then measure an angle, right? We know that if I'm given an angle, it has some measure. Now, do I know exactly what the measure is going to be? No. We're not actually going to bust a protractor out and actually measure it. Again, I'm using the title of the protractor, that tool, to say, hey, we know that we can associate measure of angles with this idea of a protractor. But remember, like with the ruler postulate, it had two clauses. The protractor postulate also has two clauses. It can measure and it makes measure. So down below, let's say I had angle ABC. I can measure out angle B there, or angle ABC, and I find it measures 60 degrees. Okay, so it has a 60-degree angle. But I can also make measure, which means, let's say I start off with a ray EF, right? I start with a ray EF, and I say I want to make a measure of 150 degrees. So I then I can actually think about, finding that rotation of 150 degrees and then creating a ray ED such that coterminal, which means having the same endpoint, that coterminal ray produces the angle of the given measure that I want. So again, these two kind of hand in hand, ruler postulate, protractor postulate, we can sum them up in very quick phrases as being able to measure and make measure. Is what we can do with both of those. And just like then, well, with the ruler postulate, we had the segment addition postulate. With the protractor postulate, we had the angle addition postulate. So angle addition postulate, AAP, you see at the top, it does simplify there to AAP. So use that acronym when you can use. What this does is that if we were to place a ray on the interior of an angle, doesn't have to be the angle bisector, just could be any ray on the interior of an angle, it divides that angle into sub-angles, and each of those sub-angles have measure, which means if we add each of those sub-angle measures together, it equals the measure of the whole. That's what it's saying down below. If point P lies in the interior of an angle ABC, then the measure of angle ABC, the whole angle, is equal to the sum of its two smaller angles, measure of ABP and PBC. There's going to be a neat consequence then with having measure being positive. Let's discuss that consequence in here in just a second, but let's talk about what we can do with our lengths, our actual measures. Measures are comparable. When you bring two measures together, you're going to find that you're going to be able to compare those. Are they going to be equal? Is one measure going to be greater than the other? And so let's talk about what it means for a measure to be greater than. How we actually understand greater than, it means it's compared to equality first, right? There must have been established equality. And then once we have an established equality, then we can call one measure greater than the other. So let's say we have a quantity we call A, which is this, you see that it says, we say that quantity A is greater than quantity B. So in order for me to actually declare A greater than B, I have to know an initial relationship about A and B. I have to know that there is some positive quantity P such that the value A is equal to B plus P. So that first kind of a statement before the semicolon there, that is all needed. We actually need to establish what equality is first between the two. And if we have A and B, this relationship says that B needs a positive value added to it. So, right, think about that. B needs a positive value added to it. That means I know A, we can define this to say that A is greater than B because B needed more, right? B needed more positive value added to it to increase its value such that it could be equal to A. And in turn, we can actually also say that B is less than A with this because B needed more value added into it to then equal the value of A. So down below, we see an example of this, where if we let A be the number 12 and B be the number 7, well, then by definition of greater than, we know that 12 is greater than 7. Here's why. Because 7, which is our B value, required more value to it. So we added a positive value 5 to 7 to make it equal to our A value, which is 12. So then, by definition, we can say 12 is greater than 7, or likewise, we can say 7 is less than 12. All right, so we actually kind of get a 2-for-1 deal out of that, of using the terms greater than and less than there. So why is that important? Well, because all of our lengths, all of our measures for angles and for segments, they're positive, which means the segment addition postulate and the angle addition postulate, it lets us compare the whole to the part, right? Think about what those two said. You took these two subparts and added them together to equal the whole. And since we know both subparts are positive, that means it required additional value, right? Additional positive value added in to equal a larger positive value. And so that means we can actually compare, and it's really easy to say then that the whole is always greater than the part. So let me say that again. The whole, as in like the whole segment or the whole angle, is always greater than the part, as in the subangles or the subsegments that are then are constructed. All right, so we now go to back in time just a smidge to talk about the definition of a straight angle. A straight angle, remember, it's only the inherent properties that it has. The inherent properties of straight angles say this, that the two rays, right, the two sides of the angle make a line. That's it. There's no mention of its measure, because right now angles inherently don't have measure until we associate a measure to them. We give a measure to it. And so the straight angle postulate is actually this idea that we are giving measure to the straight angle. And so what this is saying is we are giving the measure of 180 degrees to all straight angles. We say all straight angles measure 180 degrees and only straight angles measure 180 degrees. So if I were to make a statement and I was pointing at an angle, let's say this angle right here, and I said, hey, that's a straight angle because its side form two lines. I'm right, but not by straight angle postulate. I'm right because it's by the definition of straight angle. But if I point at this angle, say, hey, it's straight, and that means I know it measures 180 degrees, that's not by definition. That's by the postulate. So we are going to need to make sure that we don't blur those lines, that there are two different things going on here. There's the inherent properties the object has, which is the definition, and there's the properties we associate with the angle, which is this postulate right here, the straight angle postulate. And notice there's no simplifying this one. Do not write SAP. If you write SAP, that's segment addition postulate. This is just simply straight angle postulate. Now, what does this do for us? Why are we introducing these other tools? Well, these are actually what we call engines of inference, okay? Engines of inference. So what does this mean? What does it mean to actually have these engines? Or what does even inference mean? Let's talk about that just for a second. So inference means that we're able to draw a conclusion from a previously made statement. So, for example, right, if I were to say that I were to hand you an acute angle measure, what then is something that you can inference from knowing that you have an acute angle? You then can inference, oh, I can inference that the angle must be greater than 0 but less than 90 degrees. So it's something that follows from the first statement. That's something that follows. And so you have to be really careful about inference because we want to make sure that we're drawing a true statement from another true statement. And really, truth begets truth, right? And that's what we're trying to follow. We're trying to follow what is the truth following from the first, right? So if I were just make a statement, I could say, hey, angle ABC is straight. Well, then what is an inference that I can make from knowing that I have a straight angle? I can actually make two inferences from that. I can say that its sides form a line. That's an inference of its definition. But I also can make an inference from the postulate and say it measures 180 degrees. So there's actually two inferences that I can draw from having one statement of knowing that an angle is straight. And so we're going to practice this on the last couple of slides of I'm going to make a statement, and then we're going to practice see is the second statement that follows, is it a proper inference? Did I actually correctly draw a proper inference from the first? So let's start with our first example here, all right? So the first, so in the italicized sentence below, there's going to be a sentence being stated, and that's the first statement. Then after the period, you're going to see the word thus. Whatever follows that, that's the inference that I'm making from the first statement. And we're going to check, Is it a genuine inference? Is it something that is actually true that I can appropriately draw truth from and say this is absolutely going to be true? And so we have to be really careful here. So let's say for our first example here, we have points F and G are given. Thus, so the first statement's given. Thus, here's my inference. A unique line exists that passes through them. Well, is that a true inference? Yes, and here's why. We can reason it. We can say yes, of course it follows. It does follow from the first because of the line existence postulate. Given any 2 points, there exists a line, and that line that passes through those 2 points, it is unique. So yes, if I are given 2 points F and G, thus a unique line exists that passes through them. Perfect. So I can justifiably say that is a properly true, genuine inference. Let's do this again. Angle 1 is right. Thus, angle 1 measures 90. Well, is that a proper inference to draw from? If I hand you a right angle, can you then say, oh, then I know that the angle 1 measures 90? Of course it does. Yes, follows by the definition of right angle. That's how we define a right angle. It is this specially measured angle that has 90 degrees to it. So that's a proper inference. Here we go. A third one. Angles 1 and 2 form a linear pair. Thus, angles 1 and 2 are both right angles. Let's think about this. Angles 1 and 2 form a linear pair. What can I draw from that? Let's unpack the definition of linear pair. The definition of linear pair has 2 things with it. It says the angles have to be adjacent and their non-common sides have to form a line. So my inference here says my angles 1 and 2 are both right. Is that a proper inference? Just because I have 2 angles that are adjacent and their non-common sides form a line, is it guaranteed that both angle 1 and angle 2 are going to be right angles? No, that's not a proper inference. So that does not follow, right? My second statement does not follow from the first. There is no conclusive evidence that my second statement has to be true because of what was made in the first statement. So down here it says, does not follow, linear pairs need not be right. They don't have to be right angles, okay? They could be really any 2 angles that are adjacent and their non-common sides form a line. They don't both have to be right angles. Now, could they be? Yes. But to make a genuine inference, it means it has to be something guaranteed true 100% of the time that's being made or drawn from the first statement. Okay, we got a couple more here. B is the midpoint of segment AC. Okay, thus AB equals CB. Let's unpack the definition of midpoint. Definition of midpoint says that a point has to be on the segment and it divides a segment into 2 equal subsegments. So imagine this, that I have a segment AC. I place point B in the middle, which is the midpoint, which is what's given, right? That's the first statement. B is the midpoint of segment AC, so that's without a doubt true. That's what's given to us. So then does it follow that the segment AB is equal to segment BC? Yes, of course it does. It does follow because that's what midpoints do. They cut the segment in half. They actually do. They bring that point in the middle. It brings that equality out of our segment by generating 2 equal subsegments. So yes, the length of AB is equal to the length of BC because we're given that B is a midpoint. Let's be careful with this very last inference. Then it says this. So the very first statement is actually an equation. We read that equation. It reads this: that the measure of AB is equal to the measure of CB. Okay, so that's our given statement. The measure of AB is equal to the measure of CB. So here's my inference then. Thus, B is the midpoint of segment AC. Is that true? Is it guaranteed that because I have AB is equal to CB, that B must then be the midpoint of AC? No, and here's why. We don't even know that point B is actually on the line segment AC. Remember, think about what the definition of midpoint says. It actually has these 2 statements. It says point B is on the segment and it cuts the segment in half. Well, we're not told that point B is actually on the same segment as AC, so we don't know that A, B, and C are collinear. So if I'm told that AB is equal to BC, well, does that mean that B is on the segment? I don't know. There's no conclusive evidence. Let me just quickly sketch just a quick diagram of what this could look like. I'll put that up here at the top where I have some space. So let's say that's point A. We can make that point B, and then that's point C down here. So that's A, that's B, that's C. If I was told you that A, B, and BC are equal, is it guaranteed that B is the midpoint? No, right? That could actually have been a triangle, and I could have been saying that the 2 sides of the triangle are equal. So is it possible that B is on the segment? Sure, it's possible. But remember, to draw a genuine inference, it has to be 100% true of the time. 100% true. And we'll be practicing drawing inferences on our homework assignment. So when you get the worksheet, you'll find that I've done the first few problems for you. Now, there's a lot of text above that I want you to read on the worksheet. Make sure you read through all that text before you get to the problem set. Once you get to the problem set, you'll see I've answered the first several for you just to give you an idea of drawing proper inference. You are going to practice drawing proper inference using two of your tools. You're going to start now seeing definitions being used as tools, and now we've introduced a bunch of geometric postulates. We have some more postulates introduced in our next lesson, and we'll get to those. They're going to be more of along the algebraic sense of postulates that we see. Okay, so that concludes the lesson on 1.6 geometrical postulates. If you do have any questions, do not hesitate to email me. With that, be good and do good.